Hello, folks. It has been a while. I have not done one of these book club sessions in, I think, 7 weeks, which is the longest period since we started them almost 2 years ago. Um, it's been a busy time. I have some cool things I wanna share with you, but I'm glad to uh, I'm glad to start this again, and we'll do a quicker session today. I don't see anyone on the live stream yet, so I'll just talk to the asynchronous audience that tends to watch this later on. So today we're going to talk about fine-tuning, large language models in particular. I find fine-tuning to be one of the most fascinating parts of LLMs because it's where you get to make the model what you want it to be, or the creator largely gets to shape the majority of the model. In the previous sessions when we talked about pre-training, there's not a lot of control that goes into pre-training. The model learns from large corpuses of text, but fine-tuning is where you really get to shape things like the tone and the identity and expertise, whether it's good at general language or coding or what may have you. So fine-tuning is likely most relevant for you as a developer or as an individual because it's where you get to make the model good at whatever you want to make it good at. And it's also, as you'll see later, one of the areas where most people are likely to apply their efforts in large language models. So with that, let me jump into it. I'll share you what I've been working on. I've gotten to work on this new model, Gemini, at Google, and so I've switched to a new team. It is the team that works specifically on a lot of these model related things, so I'm very excited about that. That's where I've been spending a lot of my time onboarding and meeting new folks within the company. But I don't want to forget about again this book club, so we'll try and have these more regularly in the new year. In terms of fine-tuning, I'm just going to go through this chapter I wrote, and we'll cover some highlights, and then we'll leave it at that. All right. Nitesh, good to have you again. It's good to have see some of the folks that have not been here, or I haven't been here for a while, so it's good to see a lot of these folks come back. So I'm glad to see you. What we're going to talk about today, if you haven't seen already, is fine-tuning. So let me start. I think the easiest thing is let me start with a comparison. I've done a pre-recorded video so you can see what the difference is. But let's pull this up and let me let it run. I'm going to put the video link into the chat as well so you folks have it. All right, so I'm going to let this run because it's going to do a better job than me. Let's take me off screen for a second. Oh, 1 second. Let me turn the audio on so you guys can hear it. All right. What I'm going to show you here is a pre-trained model versus a fine-tuned model. We're going to run both the Llama 2 pre-trained model against the Llama 2 fine-tuned model for a one-to-one comparison. We'll go ahead and load both models. We'll ask a very simple question. How do you make eggs? On the left, we get the pre-trained response. We get something about eggs, but not exactly what we're looking for. And on the right, we have the fine-tuned version. Much more what folks are looking for these days. Which is why all commercial models that you see have been through many, many iterations of fine-tuning. All right, and so that's the demo. And that's the difference between a fine-tuned model and a pre-trained model. If folks want me to run a couple more examples live because we're in this book club, let me know. But it's this big difference. Fine-tuning. Oops. Let's go back 1 second. It's this difference. Even with a simple query, the pre-trained model it gives you some text, but it's not super helpful. Pre-trained models are actually not that good at what is typically referred to instructability from the Instruct GPT paper. They just tend to want to complete a lot of text, and they don't. It seems more like a rambling sort of person that's lost coherence of the world rather than the chat or conversation that we now expect from largely fine-tuned models. Now, this is an example of, let's say, a natural language query of how to make eggs, but it'll be the same thing if we try and do, let's say, how to generate Python code or write a SQL query or anything else like that. Pre-trained models don't seem to provide super useful output. It really takes this fine-tuning step to make them as good as the models we now have come to expect in sort of the post-ChatGPT era, where a lot of folks have interacted with language models. That motivates pre-training, or that motivates fine-tuning. The question then becomes, how does fine-tuning work? So what we'll cover is how does fine-tuning work sort of in the high level, and then what are different fine-tuning strategies and why are there different fine-tuning strategies? I'm going to point out fine-tuning is one of the fastest moving areas of LLMs for a number of reasons. The first one is the usefulness that we just saw, like fine-tuning is absolutely necessary. So the question always becomes, how can we do it better, and how can we do it more cheaply? And then how can we obviously scale it? Those are three different sort of dimensions for fine-tuning. So the way fine-tuning works in aggregate, a lot of times you have prompts, weights, you get a model response, and then there's some signal of how good this answer is. And then some weights are updated. So in this case, I say, what's your name? I'm Raveen. And that seems okay. So maybe we don't want to update the weights. But like you saw in the eggs example, if you say how to make eggs, you get what looks like a bunch of gibberish. So we definitely do want to fine tune, which is why Meta spent millions of dollars fine tuning using a variety of techniques. As I mentioned, fine tuning actually isn't one method. It's a bunch of methods, and they're not mutually exclusive. Different fine-tuning methods that we're going to discuss below can be stacked or moved or mixed around together. But I found largely it's these questions that people are trying to answer when they're picking which fine-tuning method to use. So how different of an output do we want? Sometimes we want a very, very precise output, so maybe it requires much, much more fine-tuning or a more efficient version of fine-tuning. There's always the question of compute and human expertise. How many GPUs do you have on hand, or TPUs, or whatever it may be? How much human expertise can you afford in terms of ratings, which we'll talk about in a second. I should put time on here as well. With how fast things are moving, sometimes you don't have 6 months to wait for your fine-tuning job to run. You need things to run quickly so you can get your model updated out there. There's also the question of reusability, and I should say fine-tuning. How reusable do we want our fine-tuning investment to be? And then how complex can we have the implementation be? So in large organizations, you have a lot of folks. You can deal with fine-tuning methods that are very complex, but at home, or if you're training your own model, most lay people likely want a fine-tuning method that's easier to use. So with those considerations, let's jump into a couple of methods. I'm going to breeze through them, so this might be one of the shorter book clubs that we do, but let's go through it. The first and most obvious fine-tuning method is what's called supervised fine-tuning. The way this works is you prompt a model, you have a model response, and you have a true response. So two things have been constructed: the prompts and the response set. So what should be prompted and what the model should respond with. This is just like supervised learning from the machine learning days, or even just regular statistical methods. Always ground truth and then objectively true answer. This method is very easy to understand. The challenges of supervised fine-tuning, though, are you have to construct both the prompt and the response. So somebody has to both write the input and the output, and they have to write a lot of them together. What this means in practice is that if you want your model to be very good, you have to find a lot of very good humans to write a lot of very good prompt output response pairs, and that isn't as easy as it may seem. The best writers are rare and expensive, and so constructing tons of these is not as easy, because you again have to create the whole thing yourself. On the upside, though, is it's not too bad to implement. The way supervised fine-tuning works is you end up with a loss. You end up with a distance metric between the generation that is this previous one, and then with one that is the true response. If you remember from pre-training, we have the log probability of each token being produced. That gap ends up calculating the loss, which we then can send to the model weights, update the model weights, and then get our new answers. So in here, I put the references per section. The Llama 2 paper is a very good example of supervised fine-tuning. Has a lot of good examples, and you're going to see the Llama 2 paper referenced a lot because it's one of the few papers that shows really the details of a very large-scale supervised fine-tuning examples. So here we go. Here are 2 supervised fine-tuning examples. SFT as it's shown at the bottom, of 2 different classes, helpfulness and safety, and these were part of the mix that that Meta used. They have a nice section on quality is all you need, and they show that different platforms and vendors have different performance. So they had to validate a couple of these examples to make sure it was the best. This again is the challenge with supervised fine-tuning. Nitesh asks, is supervised fine-tuning susceptible to overfitting, as we probably have less supervised example than in the unsupervised stage? That is a very good point. Okay, so I want to talk about that one specifically. You are right; it is prone to overfitting, but sometimes that's a feature, not a bug. So I'll give you quite a good example. Let's go to OpenAI if I still am logged in. All right, so this is an example where you probably really want an overfit. Oh, and I'm not showing you my screen. This is an example where you probably want a really good overfitting. So let's ask ChatGPT, who developed you? We're very sure that when we say, what's your name? The response we want from ChatGPT is, I am called ChatGPT. And we really want to know, when we say who developed you, that it's probably going to be OpenAI, or at least that's what OpenAI wants. So this is a case where supervised fine-tuning is quite useful because you really precisely know exactly what you want this model to say. So in my case, if I'm making a ravine bot, if people ask, what's your name? I want a lot of examples that say, my name is Ravine, because there's a very clear answer here. So very astute question, because while supervised fine-tuning is, let's say, the most obvious solution if you are trying to change the outputs of a model, especially if you come from, like, let's say, classical machine learning, it very much constrains the model of where it can be. And so I have this point here. It doesn't give a lot of flexibility for different generations that may be equally good. That's a really good lead-in into the next and most, I have to say, one of the most popular methods of fine-tuning now, which is called RLHF, or reinforcement learning with human feedback. So I'm going to read off what I say here, because this is the kind of the core idea and hits exactly your question, Nitish, which is in RLHF, instead of telling the model exactly what to say, which, as you noted, can cause overfitting, we just want humans to share what they prefer. So we don't want the model to memorize exactly the firms and output input responses that we provided it. we want the model to give responses that humans tend to like. It's subtly different, but it has two key things that make it better. Or RLHs have two key properties that I think have made it more useful, in at least my experience, and what the Llama folks have said in their published experience as well. One is the thing here again, from a modeling perspective, we don't want to overfit, and from a from a modeler's perspective, we don't want to overfit, and from a user's perspective, the user probably doesn't care about one specific generation. They care more about what something they just like. So if we ask for a recipe of eggs, they probably just want useful recipes, not a very specifically written recipe. The way RLHF works and the way it does that is there's two setups. In a single-sided setup, we provide a prompt, the model outputs a response, and then a human reads the response and provides a rating. So in this case, what's your name? My name is Raveen. The human rater might say this is a 3 because it's correct. Maybe a 4 would have been, my name is Raveen, and who are you, and what's your name? Or my name is Raveen, how can I help you today? If we wanted a model that was, let's say, more helpful. So a human rater provides this numerical score. That's used to update the weights. The degree of the score indicates how much the weight should be updated. What's also quite common these days is what's called a double-sided setup. A model generates multiple responses. I'm Raveen. Here's how to make eggs. And in this case, the human rater just provides their preference rating, what side they prefer, and often a degree of how much they prefer that particular side. This again goes back and goes to the model weights. Now the second benefit of RLHF, and it's a benefit above supervised fine-tuning, is as humans, think about when you're eating food at a restaurant. I can go to two restaurants. I can go to a restaurant, let's say in the US, I can go to like a McDonald's restaurant or Burger King. That's pretty good. I don't think it's bad. But I can also go to a super good Michelin-starred restaurant that has the best meals ever. It's so tasty. And then let's think about it from two perspectives. One is the perspective of me just saying, which one do I prefer? I clearly prefer the Michelin-starred restaurant, like 99% of the time. It is very good. The meals are super tasty. It's very easy for many humans to provide their preference for, let's say, food options. What's much harder is actually creating the Michelin-starred meal. So in supervised fine-tuning, I would have to show the model how to create this Michelin-starred meal by actually doing it, writing something that is very high quality. Very few people in the world, a much, much smaller percentage, like orders of magnitude smaller, maybe less than 1% of people have the capability to create a training example of a Michelin-starred quality type of meal. It's very hard. It takes a lot of years and skills to make. It's much easier to create, to just say which one do I prefer between one meal or two meals. It's that idea which makes reinforcement learning actually quite useful. Reinforcement learning with human feedback. Collecting human feedback is much simpler, and you can send that to a much broader array of people than you can for people to create supervised fine-tuning examples. This again is noted in the Llama 2 paper. I'm going to keep pointing to that paper because it really talks in detail about some of these challenges, and there's a section in there where they talk about how getting those high quality supervised fine-tuning examples is challenging, and also how once they reinforcement learned with human feedback a model, they actually can generate SFT examples that are just as good as the ones they got from written humans. So we'll come back to that point about AI generated examples in a second. But for RLHF, I'm going to point to these particular papers again. The one other paper I want to highlight that isn't sort of a famous paper, but something that I found quite useful, was this paper that talks about reinforcement learning with human feedback limitations. So many modeling papers, they tend to tell you the output of RLHF and that it worked and it was good and it helped their model. So you see the positive side of it, But this paper does a good job doing an overview of the landscape and talking fairly just about reinforcement learning with human feedback itself, and the benefits and the challenges. So if you're really interested in RLHF, I would suggest reading this paper either first or exclusively, because it is focused on RLHF. It doesn't just tell you the good parts, and it's not just introducing the method. It's collected a lot of the other research and feedback that's out there, because this one is published in 2023, just recently 2 months ago. Oh, here we go. Just recently 2 months ago. The other paper, which is interesting for historical purposes now and has some nice diagrams, but has been superseded, is the original Instruct GPT paper. This was the paper from OpenAI way back in, I think, 2000. Well, now this feels old, but early 2002, almost 2 years old now. And it's the one that really kicked off a lot of these RLHF focus. And not totally, because there were other ones before that, but it's the one that I keep seeing cited as like sort of the canonical paper for human preference alignment on models and how it works. Since then, a lot has changed, so I suggest reading this one first. And then for practical examples in models, both, as I mentioned, Meta and Anthropic have released papers showing the benefits of RLHF and how it worked for them. Okay, so now we have two methods. We have supervised fine-tuning, and we have RLHF. I'll pause here and say, you can mix and match these two methods together, as you see in the Llama 2 paper, and even in the Anthropic paper. You can go through a round of supervised fine-tuning, then you can go to RLHF. Then if you want, you go to supervised fine-tuning. They're not mutually exclusive. What I've seen in practice, at least up until now, is typically there's a pre-trained model, then there's supervised fine-tuning, and then there's RLHF. But there's no hard and fast rules. It's just what I've noticed. All right, the next one is reward models. So in the last two methods, humans have provided either a prompt response pair output, or they have provided their preference. So you have to have people that are available to help provide their preference. But the question then becomes is, can we then have AI teach AI? And the answer is yes. Another common pattern now for reusability is what's called a reward model. You don't just train one model, which is what we'll call a user model. You actually train two or more models. So you have your pre-trained model, and then to train that pre-trained model, you have what's called a reward model that outputs scores rather than the next token. So in the model we're going to ship, you have token outputs, so those can be translated into text, whatever it may be. So a human can read it, but a reward model has a very similar architecture up until the very end, where instead of providing for prompt another set of language outputs, it provides, again, a score. That score goes and it updates the model. Now the question may become, where does this model learn its preferences from? It learns these preferences from humans. So now you're training two models. You have your original model that you're training, but you also need to train a reward model from human preferences. Typically, from what I've seen, is it's RLHF. The good news, though, is once you have that reward model, you can reuse it over and over and over again. So once you've trained a reward model, you don't need to then send the next, like, let's say you train a reward model on 1,000 examples. For the next 5,000 examples, you don't need to send them in front of humans. You can largely automate human preference through a reward model responses. So again, this is a very common pattern. You'll see, I'm going to point to the Llama 2 paper once again, and there's a nice. I have so many papers now. Let's see. I'll remember this one is Llama 2. They provide a very nice diagram here showing their full loop. We've actually now covered every single piece of the Llama 2 example. They do a large level of pre-training. They then copy this pre-training model, and one of them turns into the chat model. They supervise fine-tune it first, but after the supervised fine-tuning step, they go in and they have human preference data that trains two reward models, in the paper, they tell you that these two reward models are actually the Llama 2 variant here. Now with the token output head replaced with a prediction head for numerical scores. That's used to fine tune. They do some types of fine tuning where they sample multiple times and do rejection sampling. But the idea is the Llama 2 chat model produces some outputs. The reward models, which have been trained, provide feedback. They keep doing this. They actually do this 5 times, and then you end up with Llama 2. So now you know, these are the reasons I actually chose these 3 fine-tuning methods. These actually aren't the only 3 fine-tuning methods, but they're the ones I keep seeing over and over again, which is why I'm pointing them out in this guidebook, because I'm trying to guide you to the most common methods. I'm going to keep barreling along here because I don't see any questions. The next one I throw in here is constitutional AI. I put this one in here because I'm going to say because it was written by Anthropic, and because it shows you how far you can take this reward model idea. And at least Anthropic is I don't want to say they're putting all their eggs in this basket, but they're big proponents of this method that they've developed. The essential idea is that I'm going to have to go through each step carefully because there's a lot of steps, and I might get a couple wrong, so don't quote me from memory. But the idea is, instead of a human telling people exactly the prompt output response pair, or humans telling the model which ones they prefer, or just training a reward model based on human preferences, you do this thing called creating a constitution. So you tell a model that already has some amount of fine-tuning, you tell it what it should be. That it should be, in this case, as Anthropic's diagram shows, that it should be harmless, ethical, and virtuous. So you have the model generate responses to what's called like harmfulness prompts. You have the another model, or I think it's the same model, critique and respond to its own generations. You then use the critiques and responses to fine-tune another model. That fine-tuned model generates preferences for harmfulness data, for harmfulness responses. So which is more harmful, which is less harmful. You then train a preference model, and then you fine-tune another model. I'm going to show you their paper because it has a nice diagram in it as well. Not as visually as attractive as the one we just saw, but it is this one. It's this diagram here. They talk more about it in section 2, but it is multiple models in multiple steps. The idea just generally being that the models self-critique themselves through a sort of chain of thought process on what's better or not, generate 2 sets of pairs of samples. Another model is then improved, and then you have what's called finally the reinforcement learned constitutional AI model. This is how Claude is trained. The core idea here, going outside of the details, is we just need to provide the model a small constitution of what it should act like, and then in a mostly automated fashion, we can then get a very safe model that's trained and outputted. There's a pretty complicated graph here from Anthropic showing that if we take a helpfulness score, and we have a helpfulness and harmless sort of diagram. So Anthropic's all about helpfulness, harmlessness, and honesty. It's their HHH model. Their HHH's paradigm, I should say. If you have a pre-trained base model, by using constitutional learning, standard reinforcement learning will only get you to this barrier right here, where it's helpful. The model is very helpful, but it's still probably super harmful. When you go to helpfulness and harmfulness, there seems to be from the research, there seems to be an increase, but then things tend to drop, at least in the harmlessness area. But with constitutional reinforcement learning, we end up in this new barrier up here with chain of thought reasoning. The model is both very helpful and very harmless. They placed a lot of research into this area and branded it, so you see this idea come from them quite often. But more generally, it's this idea that can we give a model a small set of principles and have it figure out itself how to be helpful, harmless, or whatever else you may want a model to be. All right. So we're at the midpoint of our book club now. I've covered the fine-tuning methods, the aggregate methods that I've seen the most often. There's now some more. There's new ones coming out, so I'm going to even update this already because there's another one called like direct preference optimization, if I remember correctly. It's called DPO. Let me find it for you. Yeah, so it's this paper here in this method called direct preference optimization that just came out early this year. It is being used more and more and more, and I'm seeing it show up more and more and more. It looks like this one comes out of Stanford, so not an AI lab, but from a university. So I'm going to add a section on that later, but I just wanted to note that while I don't want to give an off-the-cuff response right now, it just seems to be showing up much more and more. Oh, I'm not showing you my screen. Here we go. Direct preference optimization. Here's the chart, and here's the paper link. And I will update the book club, the book guidebook later. The reason I say this is the midway point in our book club for today is we've been talking about methods that update, and as I've been implicitly saying that we're updating all the weights, or I haven't mentioned what weights we're updating. So the next part, in the next 20 minutes, what I'm going to talk about is what's called parameter efficient tuning. The reason it's called parameter efficient is that if you're fine-tuning an entire model, it takes a lot of compute. These new models are huge, like 70 billion parameters from Llama 2. So it's very hard to fit into memory. And not only do you have to fit your original model into memory, if you have reward models or constitutional AI, and then also if you're not just doing forward passes, but you're also calculating the gradients backwards, that just takes even more memory. It takes even more compute. So for folks that don't have supercomputing clusters at home, which is almost basically everybody because your whole house would be a data center at that point, it's not practical to retrain into all of Llama 2, like the 70 billion parameter model, yourself. It also is, even if you're a company, it's very expensive. So it takes a long time to then determine whether your fine-tuning worked, and it takes a lot of electricity and money. So a big question is, how few weights can you train to have the biggest effect on your fine-tuning? So that, again, is parameter efficient fine-tuning. So let's talk about the couple methods that I've seen been used more often. I'm going to point out that there are many parameter efficient fine-tuning methods. If you go to the library from Hugging Face, they have 11 listed between prompt tuning, LoRa, prefix tuning, and others. Some of them are for image generation, which we don't, and diffusion models, which we're not talking about as much over here because we're focused on large language models at the moment. But even aside from this, there's even more in paper and in research. Parameter efficient fine-tuning, again, being a super hotbed of research that is a parallel work stream to fine-tuning methods. So the first one I want to talk to is prompt tuning. The basic idea between prompt tuning is it's like, what has the biggest effect on model generation? Well, you have 70 billion parameters. And arguably that changes the prompt output a whole lot. That changes the output a whole lot. But the other thing that changes the output is the prompt, right? It's whatever you're providing the model to kickstart text generation. So it behooves you to think that the weights that would have the most effect are the ones that are closest to the prompts or interact with the prompts. So that's what happens with prompt tuning. What you do is you take your model and you bolt on a series of weights that go between the prompts and the models, and then you only fine tune these particular weights right here. So if we take the T5 model, which is a Google model, I believe, the original model had 11 billion parameters. So they were quite a bit. But if we just bolted on some additional parameters, I think this should be 20,400. I apologize, but if you bolt on another just 20,000 parameters, it changed the model dynamic very, 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 very much. So, did I? All right, I need to add in the prompt tuning paper here to show you. But again, you don't need to update all 11 billion parameters weights. You just need to add on sort of a middle layer of weights that are around 200,000 in size, which is much less than 11 billion. And you're able to change the model responses quite a bit. I want to highlight this is different than prompt engineering. Prompt engineering is changing the prompt itself to elicit a different model update. The reason I'm not considering it a fine-tuning method, and I'm pretty sure it's not considered a fine-tuning method in general, is there are no weights updated in prompt engineering. You're just updating the prompts, and the model weights stay exactly the same. So very, very similar ideas. The prompt is a big lever in changing the model output, but in one mechanism, you're training some weights that interact with the prompt directly. In the other, you're just changing the prompts and updating no weights. Let me actually show you this blog post real quick, because I think it had some very nice figures. Yes, so here's another figure, which similar to the one I had. You have the large language model weights that have largely been frozen, but you have another prompt tune model that takes in the prompts and alters the weights before they get to the LLM themselves. There's another paper that has very nice has a nice diagram of how this works. I'll see if I can find that again for you folks. Actually, maybe I'll just go here and it's here. It's the Hugging Face model. So it is right here. So again, you have a pre-trained transformer and you're bolting on some weights at the beginning. These are the weights that are being trained. You're leaving the original transformer weights fixed. All right. So we have those two. The other one, which I'm seeing quite often, is this one called LoRa. And not just the original version of LoRa, but now different variations of LoRa. LoRa stands for low rank adaptation of large language models. That's where that LoRa comes from. To fully understand it requires a lot of linear algebra, but let me just give you the quick version, and then if there's questions, feel free to ask in chat, or for the folks that come in later, you can ask through comment. Large language models have a lot of parameters. They have many parameters. Like, arguably, they could have more parameters than they actually need. So let's say with the Llama 2 model, for instance, there's a 70 billion parameter version of the model, and then there's also a 7 billion parameter version of the model. So it begs the question, like, do you need all 70 billion parameters to have this space to do the mathematics that you would like to be able to do? The people who came up with LoRa arguably said you don't actually need this massive parameter space. What's happening in a large language model, they argue, is that in many generations, it's actually just using a small subset of the space to then provide the actual generation. So maybe if you're asking about code, it's using a subset of the weights and the subset of the entire linear space. If you're asking about creative writing, it could be using another subset of the weights. So their idea was, in linear algebra terms, you have this thing called matrix ranks, which represents the rank of the matrix is how many linearly independent, I believe, rows and columns you have. I'll point you to the Wikipedia article in a second. But if you have repetitive matrices, a large matrix that has very low rank means it has very little information in them. With large language models, instead of having to train the full rank matrix, which is the entire large language model weights once again, you can use a bunch of clever linear algebra and linear methods to add on weights that collapse, that are trained at a much lower rank, which means that they're much smaller size, but they don't give up their ability to influence the generations, even though they're a much smaller size, because of this idea of matrix rank. Where it's denoted in the diagram that I've adapted for them is you have, let's say, a generation that's say of length d or of dimension d. You actually only need a much smaller and in a matrix of rank r to finally then output a very different generation back in the original space that you wanted it to be. And because of the properties of linear algebra, you can then just bolt on a much smaller amount of weights to a larger amount of weights and still get high quality generations. DTS asks the question, does that mean LLMs behave a lot like linear models since we're looking at them at lower dimension linear projections? Okay, you actually worded this much better than me. LLMs are basically a bunch of linear models. When we looked at the pre-training section, if I go back to that, I won't go back to it now, but LLMs are just a bunch of matrices put together, right? Like all the actually I will go back to the pre-training section so folks who haven't seen it can see it. If we go to I need to add my references. This is where it's my transformers overview. Okay. If I go to Flax, I really want to show this to you. Well, I'll just show you GPT and 60 lines and NumPy. We'll do that. All that an LLM is a bunch of these is a bunch of matrix multiplications all put together. This one doesn't show it as well. Give me 2 more seconds to show you. Attention implementation of Flax. Here we go. It's just this, right? This is largely these einsums or these dot products are just what LLMs are. So exactly as you've noticed, since we're just looking for linear, lower dimensional linear projections, that's exactly what the LoRa folks are doing in their particular paper. They're just saying, why don't we just train the model in train a set of weights that are in a lower dimensional projection, and that'll get us what we need. And it turns out it's very, very effective. If we go back to fine tuning, parameter efficient fine tuning, oops. And we go to LoRa. It turns out this method is super effective, and there are numerous implementations. The Google Cloud Docs actually provide a really good practical implementation of how these work. How LoRa, the different practical dimensions for LoRa, how different versions work, and why they recommend different sizes versus others. To give you a sense of how low of a dimension you can go, and things can still be fine. The other practical engineering benefit of LoRa is that these weights here, you can have one very large fine-tuned model, and you can train different sets of LoRa weights and bolt them in and remove them in and out. So if you're, let's say, doing a cooking tutorial, and you need the lower dimensional space, you just put in the cooking set of weights, and then if you now have another model, you now have another use case that's like the coding use case, you just plug in the coding use case, because these weights don't affect the original pre-trained weights. They're trained in a lower dimensional space that maps to a higher dimensional space, and then they just become additive to get you the generation. So tons of words. For the folks that want linear algebra, I provided some semblance here and shown you a NumPy example where in this case you have 2 matrices. This matrix is 1, 2, and then it's 3, 6, and this one is 1, 2, and 3, 5. They look very similar, but this one has a rank of 1 because this row here and this row here, this is just 3 times the first row, so there's not much extra information. There isn't any extra information according to rank. But this one here, these two are not linearly dependent. So there's no linear combination of row 1 that gets you row 2. So these two are distinct. So now you have a matrix of rank 2. That's the very, very short version. Rank becomes much more is a much deeper topic. So if you want to get into it, you go to the singular value decomposition Wikipedia page, and you can read through all the theory. But once it works super super well. Very very common method that's that's applied in many situations, many deployed LLM applications. So she says, it sounds strange that despite the nonlinear activations, the model remains largely linear. Yeah, it does sound pretty strange, and I don't have a great explanation for you other than it's a very effective way for folks to influence the behavior of large language models, and it's implemented practically in many places. I have the Google implementation here again on Google Cloud, but as I understand it, it's a lot of folks are using it within with on their local computers through again Hugging Face libraries. This one again having the similar diagram that we have a dimensionality collapse. You add these two together, and then you end up with merged weights, and then here are all the code arguments and examples to show you how LoRa works. The other quick bit about LoRa, I think in case this might answer your question a little bit more precisely, is as I understand it, it only applies to a subset of the pre-trained weights. So you don't apply it to the whole model itself. You apply it to a portion that is just linear, like an attention head, before you end up with the activations and stuff. So don't quote me on that, but from my reading, I'm like pretty sure that's what's happening. It's only affecting linear calculations in attention heads and portions in the model. I don't believe it's spanning over nonlinear portions of the model itself. So there you have it. There's two versions. Those are today. That's what we covered is a general array of fine-tuning methods, and then a couple of parameter efficient fine-tuning methods as well. To recap it once more, fine-tuning is where the model shifts its behavior quite a bit, and it seems like a very common pattern, especially for folks that are likely watching this book club, is that someone else is going to pre-train a large language model for you, like Mistral or Llama, or even within OpenAI or Google. There'll be some large pre-trained model, and then for specific use cases, you have the capability to then change this pre-trained model or even another fine-tuned model to do what you want it to do through a variety of different methods. I also see this I'm seeing this be a very active research area. I think maybe for two reasons. One, again, is that leverage. I think the other reason is that it's becoming increasingly harder and harder to research things like pre-training, because you need these massive compute clusters and millions of dollars to improve models, and a lot of researchers don't have access to that. But a lot of researchers do have access to smaller AWS instances, or university labs can have hundreds or 200s of GPUs on hand. So it's a good way to have research on very large scale models, but still be able to operate on in smaller budgets and smaller timescales. I don't know that for a fact, but it's just my hypothesis being a grad student, and what my thought process was when I was working with my advisor on different methods and different areas of research. So we're just about at 50 minutes. I always like to keep these under the hour. Thanks again for showing up. I apologize. I took 7 weeks, which was a longer amount of time than usual. I just got caught up in my new job at Google. What I'm trying to decide what the next topic I'm gonna cover is for the book club. I'm blanking on it right now. I know one of them I wanted to do was multimodal. Talk about models that can take in images and tokenize those as well, because those are quite fascinating and coming out as well. And the other one was going to be large language model architecture. So we've largely been talking about the large language model itself, but now there's I feel like the way the industry is moving is not just having a text input and output sort of chat model, but plugging these into like retrieval augmentation generation systems or function calling. So where the large language model isn't maybe directly exposed to the user, but is calling functions and other APIs under the hood. and embedding patterns and things like that. So let me know if you have a preference between either one of those topics, whether you care more about multidimensionality or function calling. But coming into this new year, it's one of my resolutions that we do this, again, go to a much more quicker cadence, ideally at least once a month. So you guys get a nice corpus of material that is up to date with modern practices. So as always, there's about a 10-second delay between me talking and you seeing things. So let me know if there are any questions. I will wait about 10 seconds to see if any remain. Nitesh says, I vote LLM architecture. Okay, then I will focus on LLM architecture for the next book club. Hopefully it's going to be right after the new year, maybe around the first or second week of January. But thank you again, then, for being here today with me. Enjoy the rest of your Sunday, and have a safe and fun new year. I will see you in 2024. All right. Bye, folks.